Black holes might simply be one of the most charming and mysterious phenomena in the universe. They are massive beasts in phrases of energy, however, at the same time, certainly invisible to us. A black hole weighing possibly 2 to 4 million times the mass of the Sun, but due to the research that was put into them over the last couple of decades, we've gone from understanding certainly nothing about them to getting to analyze more and more up close and personal. And while things have just gotten crazier, Kaku just introduced that we've finally got a look at what is inside a black hole. This new information brings light to the details the world of science might have overlooked all along. Join us as we dig deeper into black holes and unveil what is inside. Space is huge, bad. Before we get into the info of what Kaku discovered, we must speak about the firsts. Despite the fact that most folks have some idea what black holes are, there are still a few gaps in the proper information. You see, in 1916, Albert Einstein published his theory of general relativity, which predicted the existence of black holes. At that time, the idea of black holes was purely theoretical. It took another 50 years for the scientific community to discover evidence that black holes really exist. This happened in the 1960s. They had been analyzing the Cygnus constellation when they saw an oddly vivid blue star that was emitting X-rays. This star wasn't a stagnant object but was going around a giant black something. Upon further research, it was found that the X-rays were not just moving around on their own, but they were being sucked into the black object they were orbiting. Accordingly, the name black hole. This discovery was significant because it provided evidence that black holes actually exist, and they were not only a figment of Albert Einstein's wild imagination. While that was great, it also meant that there was this unreal entity in space that we urgently needed to know more about. So, researchers all over the world set to work. This black hole was named Cygnus X1, and it is located within the constellation Cygnus about 6,000 light-years from Earth. And it was no small discovery. It's about 14 times brighter than the Sun and tremendously dense, which causes it to have a strong gravitational pull. The gravitational pull is so strong that not even light can escape it. This is why it's called a black hole. The idea of a black hole is both fascinating and terrifying. It's a place of space where gravity is so strong that nothing, not even light, can escape. Anything that gets too close to a black hole can be pulled into it, never to be seen again. However, that point of danger makes it even more important to study everything there is to know about them. Was this it? Or were we just beginning? The answer ended up being the latter. After the discovery of Cygnus X1, scientists started to search for other black holes. They found that there may be near over 100 million black holes in the Milky Way alone. But because they're so incredibly hard to detect, we still don't have an exact number. Although, from the looks of it, there are several million black holes in the Milky Way in our very galaxy. That's what makes them even more important to observe. So let's break it down. The first subject with black holes is always going to be gravity. Their gravitational pull is so intense that something that enters it compresses down astronomically until it becomes a singularity. In simpler terms, black holes are like cosmic vacuum cleaners that suck everything in. One of the scariest parts about the research that's gone into black holes is the fact that if someone were to fall into one, they would get stretched to the point that they become a single line. This process would happen slowly and the person would die before the final form truly sets in. So let's just say that no one should be getting into one. But they are all around, so could we just be in danger? Even though the closest black hole to Earth is 500 to 1,000 light-years away, it's still close enough to bring up questions and concerns. In 2021, scientists were able to launch the first clear picture of a black hole, specifically the M87 black hole. This black hole was photographed several nights in a row, and with each photo, the researchers gathered more and more evidence about it. They had to stitch the individual photos together to create something that filled all the gaps. This way, they were able to figure out that there are 3 layers to a black hole. It's not just one single gaping hole of nothingness, as many people believe. Things are a lot more complicated than that. To even get to the nothingness part of a black hole, you need to make it through the first 2 layers. The first layer is called the event horizon, which, while within the first layer, is the point of no return. When you pass the event horizon, there's no turning back and you will be sucked into the black hole. It only gets worse from there on out. The second layer is the photon sphere, which is the area where light orbits the black hole. Any light that enters this region can be trapped and will not be able to escape the black hole's gravitational pull. Eventually, we come to the third layer, which is the singularity. This is where everything that enters the black hole gets compressed down astronomically until it becomes a singularity. The singularity is a point in spacetime where the laws of physics as we know them break down and we just cannot predict what happens next. At the singularity, the density is limitless and the laws of physics as we know them stop to exist. Now, what makes all of this infinitely worse is the fact that every single black hole you study will be completely different from the last. Sure, they do tend to follow the same three-layer idea, but the way they function can be hugely different. Now, if this were something else, all we would need to do is hop back on those telescopes and just study the issue at hand in detail. But with black holes, you can't really do that. Scientists can only study black holes indirectly by observing the radiation they emit and the gas and dust that surrounds them. Sending a probe like the Voyager inside a black hole isn't possible because something that enters the event horizon is pulled towards the singularity where it is compressed to an infinitely small point. So you can't exactly waste billions of dollars just to get a glimpse every time because the moment the probe gets close enough, it will just crush into nothingness. Because of that glaring problem, scientists are left with no option but to study these objects in a two-dimensional way, even though they are three-dimensional phenomena. To make matters even more difficult, there are also the two problems of every black hole being unique and the laws of physics as we know them breaking down when we try to explore the interior. Meaning that the traditional methods of scientific inquiry don't really apply to the study of black holes. That doesn't mean that the researchers haven't been busy. There are lots of different theories and explanations of black holes and, well, with each one, things get more and more interesting. One of the most compelling theories about the formation of black holes is that they are formed from collapsing stars. When a star exhausts all of its fuel, it can no longer produce enough energy to counteract the force of gravity that is constantly pulling inward. As a result, the star starts to collapse on itself, becoming smaller and denser as it does so. If the star is large enough, this process can continue until it becomes a singularity. To understand the nature of black holes in depth, NASA scientists turned their attention to the center of the galaxy M87. Astronomers found a gigantic whirlpool of superhot hydrogen gas that was spinning at an astonishing rate of 1.2 million miles per hour. The sheer force of the spinning disk of gas should have caused it to violently fly apart in all directions, but it didn't. Scientists deduced that there had to be a massive mass concentrated at the center of the galaxy to prevent this from happening. This massive object weighed as much as 2 to 3 billion suns and could only be a black hole. But that's not the only theory where black holes spin. In 1963, the New Zealand mathematician Roy Kerr used Einstein's equations of gravity to provide the best description of a spinning black hole. Kerr showed that a spinning black hole wouldn't collapse into a point as previously thought, but into a ring of fire or a thin disk. The disk would be spinning so rapidly that centrifugal forces would prevent it from collapsing. This spinning disk of matter is called the ergosphere, and it's the region surrounding the black hole where the laws of physics begin to break down. But the most interesting feature of Kerr's solution was that it predicted the existence of an Einstein-Rosen bridge, also called a wormhole. This theoretical passage through spacetime connects two separate regions of the universe or even parallel universes. The idea is that if one were to fall into a black hole instead of being crushed to oblivion, one would be sucked down a tunnel through the ring of fire and shot out a white hole in a parallel universe. To understand how this works, we need to look at the concept of spacetime in Einstein's theory. In Einstein's theory, objects with mass warp this fabric, creating a gravitational field that causes other objects to move toward them. Now, imagine a sheet of paper representing spacetime. If you place points on the paper and draw a line between them, that's a representation of how objects move through spacetime. But what if you could fold the paper in half and create a shortcut between the 2 points? That's the basic idea behind a wormhole. It's a shortcut through spacetime that connects 2 distant points in an instant. Wormholes aren't just a sci-fi idea. They're actually a prediction of general relativity. Although no one has ever found one directly, the reason is that wormholes are inherently unstable and would collapse almost immediately. But the existence of an Einstein-Rosen bridge could mean that black holes are not just cosmic vacuum cleaners but could also be portals to other regions of spacetime. So could we use a wormhole to travel through space and time? Unfortunately, the answer is probably no, not yet anyway. Even if we could stabilize a wormhole, it's unlikely that we could use it to travel faster than light. Einstein's theory of special relativity predicts that the speed of light is an absolute limit on how fast anything can travel through spacetime. However, the idea of wormholes and black holes as pathways to other parts of the universe, or even to different times, has been a subject of fascination and speculation among physicists for decades. The idea that there could be shortcuts through the fabric of spacetime allowing travel over vast distances or even into the past could potentially be revolutionary if we could actually achieve it. One of the most intriguing concepts in this area of study is the Kerr wormhole, named after the mathematician Roy Kerr, who first described it using Einstein's equations of gravity. This type of wormhole is essentially a hypothetical tunnel through spacetime that could connect two distant points, such as two different universes or even two distinct times in the same universe. The Kerr wormhole is often visualized as a ring-shaped portal, much like the looking glass in the tale of Alice in Wonderland. Walking through the looking glass transported Alice to a world where animals spoke in riddles and logic didn't always follow. In the same way, passing through the Kerr ring could potentially transport a traveler to another universe or time where the laws of physics might be very different from those we're familiar with. But the idea of wormholes as a means of interstellar travel or time travel is not only exciting, as we've glossed over before, it's also a topic of controversy and debate among physicists. Some have pointed out that wormholes, and particularly Kerr wormholes, might be unstable or impossible to traverse due to the extreme radiation and subatomic forces surrounding their entrance. Critics argue that Einstein's equations of gravity, which are used to describe wormholes and black holes, only work for gravity and not the quantum forces that govern radiation and subatomic particles. In order to truly understand the nature of these phenomena, a new theory is needed that can unite the laws of gravity with a quantum theory of radiation. Throughout the field of science, this is called a theory of everything, a single theory that can unite both Einstein's theory of gravity and quantum theory. Kaku, who is a renowned theoretical physicist, has been working on a theory of everything for many years. While there are many different versions of what this might be, the only one that has shown promise is superstring theory. Superstring theory unites gravity with the theory of radiation. The theory proposes that subatomic particles are actually tiny vibrating strings, and that the universe is a symphony of these strings. Just as different musical notes correspond to different vibrations of a violin string, different particles in nature correspond to different vibrations of a different string. One of the fascinating things about superstring theory is that as a string moves in time, it warps the fabric of space around it, generating black holes, wormholes, and other unique solutions to Einstein's equations. This means that superstring theory not only unites Einstein's theory of gravity with quantum theory, but also explains many of the mysterious phenomena that we observe in the universe. But there's something about this theory that really throws a wrench into how simple it might sound at first, but in a way makes more sense too. Superstring theory requires 10 dimensions of spacetime in which the strings can vibrate. This is quite different from the 3 dimensions of space and 1 dimension of time that we experience in our everyday lives. It's hard to imagine what these additional dimensions might be like, but physicists have developed some conceptual models that could help us understand. Imagine a 2-dimensional pond inhabited by fish that are only aware of the dimensions of length and width. To these fish, there's no such thing as height, and they can't even imagine what it might be like to live in a 3-dimensional world.